Hello, everyone. Today we have Bob Sinkovitz, SDSC's Director of Scientific Computing Applications, and he'll be presenting on performance tuning and single processor optimization. I'm really looking forward to this presentation. Before we hand it off to Bob, I want to bring your attention to Exceed's Code of Conduct. We are usually on our best behavior, but if anyone observes any kind of behavior that they think is inappropriate, please let us know at exceed.org/code of conduct. And Exceed also is committed to providing training events that foster inclusion and show respect for all. So we try to be sensitive to terminology. So if you are aware of any kind of terminology that you think is inappropriate, please let us know by sending an email to terminology@exceed.org. And so with that, I will stop sharing and hand it off to Bob.
Sorry, I need to unmute there. Thank you for the introduction, Jeff. So I'm going to be giving a very brief introduction to performance tuning and single processor optimization. And can somebody just confirm that you are seeing my slides now?
Yes, it looks good.
Perfect, perfect. So it's kind of hard for me to monitor the chat as we go along. So we have a few of the folks here at SDSC who will be keeping an eye on the chat and interrupting me as we go along. And then I'll also answer a few questions at the end. And again, Jeff, thank you for putting up the code of conduct and mentioning the terminology task force. So I've gone through my slides pretty carefully. I hope that I'm that everything is up to the current standards, but please let me know if there is anything that I overlooked. So, okay. So this is going to be a very, very quick introduction to the performance tuning and optimization. This has been adapted from a workshop that I usually give during our summer institute. And it takes about 3 to 4 hours, including time for breaks and hands-on examples. Of course, since we're doing this as a 1-hour webinar, we won't have time for examples, but let me go back here. And I'll paste this URL into the chat when I'm all done. I've put together a GitHub repo that it's very, I'm going to say very, very crude right now, but I do have a few examples in there that I have used in today's talk. And think of that as a living document. It's going to be updated over time with more examples. So I'm going to start off talking about why we want to write efficient scalar serial code. So my talk today is all about the performance of the underlying serial application. I'm not really getting into parallel computing, but the performance of a parallel code ultimately depends on the performance of that underlying serial code. So there are a few reasons that we want to write fast code. So first of all, optimizing your code is going to reduce your time to solution. So I like to say that challenging problems are going to become doable and routine calculations can be done quickly. You'll be able to do more science in the same amount of time, and it can shorten that cycle between job submission and results. Computer time, especially in high-end resources, is limited. If any of you have allocations on Expanse, Stampede, Bridges, or other Exceed machines, you know that it's a competitive process to get significant amounts of time. You're kind of getting it for free in the sense that you're not paying directly. It's already been covered by an NSF grant. But still, it's competitive. There's only so much supercomputing cycles go around. And if you're running on the cloud, you could get all the computing you need, but you'll need to pay for it. And then finally, computing uses a lot of energy. It's really hard to pin this down, but it's estimated that at least 5% of our US energy consumption is spent powering computers. So I mentioned parallel computing already. Isn't going parallel going to save me? But it turns out that first of all, most parallel applications have a limited scalability. You won't be able to run generally on very large numbers of cores. Second of all, even if your application had perfect linear scalability, there's always going to be a more challenging problem that you want to solve. There's going to be higher resolutions, finer grid sizes, shorter time step. You want to simulate larger systems, incorporate more accurate physics, have longer simulations, more replicates, bigger ensembles, better statistics. And then finally, as I mentioned in the previous slide, availability of resources and energy usage are always going to be issues. So this is a little out of date, but back in 2013, it estimated that US data centers could consume the equivalent of 34 large coal-fired plants in power each year. And the estimate at that time was that by 2020, this was going to increase to about 140 billion kilowatt hours per year. So it's a lot of energy. So anything that we can do to make our computing more efficient is definitely very welcome. Okay, so some guidelines for software optimization before we dive in. I always like to say, I think of this as the prime directive for software optimization, is don't break your code. Make sure that you're continuing to get the correct results. I've done this a few times over the years where you make a change to the code, things seem to run a lot faster until you go back and you realize that the reason it's going faster is that you broke something and you're not getting the right results any longer. Unfortunately, I've never had a case where it got into where these changes made it very far and started leading to incorrect results, but always be aware of that. Make sure that you have a test suite to go back and confirm that your modifications didn't break the code. You also want to profile your code so that you know where to focus your effort. Make sure that you don't obfuscate your code unless you have some really compelling reason to do so. So sometimes you can rewrite your code in such a way that it's faster, but it's now hard to read or maintain. And I think the only times that you want to push that really far is if you're working on a kernel on a very heavily used application. Make sure that you document your changes, especially if your new code looks different from the original. Use optimized libraries whenever possible. There's a saying in software circles that good programmers write good code, great programmers steal great code. So if something is out there, just go ahead and use it. And then finally, understand the capabilities and limitations of your compiler. And I'm going to touch on that in the next few slides. So there's a question of how much effort you should put into optimizing your code. So doing performance tuning and optimization, it does take time, it does take effort, and you really need to decide, should you even get started, and how much effort should you expend on this? So I like to ask myself a few questions. Is the code heavily or widely used? If it's a code that's being used just in your lab, and it's really not that critical, if it's running a little bit longer than you need, your time might be better spent just working on your research. On the other hand, if this is a community code, if it has widespread use, if you plan to be using this for years, definitely put in some time to make it run fast. Related to that, does it consume a significant amount of computer time? Is the time to solution important? If you have a code that, say, runs in 15 minutes, you might be able to optimize it so that you get a solution in 5 minutes or 10 minutes. That's great, but does that really revolutionize the amount of science that you could do? Will optimizing help you solve new sets of problems? And have you reached the point where most of the computing occurs in routines outside of your control? So before you dive in, if you do decide that you're going to start profiling your code, start optimizing your code, you definitely want to profile first. So modern software can contain many thousands of lines of code. So profile it before you get started so that you know where to focus your effort. And when you do this, make sure that you're profiling on a realistically sized problem. Sometimes if you strip down your test case to something really, really small, you'll find that the routines responsible for input and output at the start or setting up the problem are accounting for the majority of the time. You really want to make sure that you're doing a realistic test case when you're profiling. And You're, and you're often going to find that most of the time is spent in a relatively small number of routines. In fact, I've had a few projects over the years where I've done performance optimization where it was really just a single routine. And even then, a few loops within that routine that accounted for most of the time. So there are a bunch of tools out there for doing profiling. My favorite is something called gprof. This goes way back to 1982. I think this is a great place to start. It's universally supported by all of the major C, C++, and Fortran compilers. In fact, I've never come across um, a, come across a C or Fortran compiler that doesn't support gprof. It's very easy to use. All you need to do is compile your code with the -pg flag, run the code. You're going to get a file called gmon.out, and then you just run gprof followed by the name of your executable followed by the gmon.out, and it introduces virtually no overhead. I should mention that gprof is not a tracing tool, and it's not going to identify bottlenecks in parallel codes, but that's not what we're interested in right now. We're interested in boosting the performance of that underlying serial code. And if you give me just one moment, I'll be right back. I've got a barking dog in the background. Okay, sorry about that. I'm back now. So next couple of slides, I'm going to demonstrate, I guess, how to interpret the gprof output. gprof has two main outputs, is what we call the flat profile and the call tree. So the flat profile is just the listing of the functions and subroutines ordered by their relative use. And again, you're often going to find that it's just a few of those routines that account for the large majority of the time. So this is very handy for identifying those hotspots in your codes. So this is an example from an application that I had worked on, which we're going to be revisiting a little bit later, in an area called flow cytometry. This was with one of my collaborators at the J. Craig Venter Institute. So we got the original version of the code, we profiled it, and we found that the majority of the time, just about 69%, was being spent in this routine called get number pack data, and then followed by main and quicksort and a few other routines that are adding negligible amounts of time. gprof also produces a call graph which shows which routines are called by other routines. This is handy, especially if you're going to get into inter-procedural optimization, which I'll get to at the near the end of this talk. So starting at the top, we see that the routine main is called once, and then it will call get number pack data 399,000 times. It also calls routines called isHump, quicksort, radix sort, and ID2 center. Then we get down to the next routine. We see get number pack data. We see that it is called by main, and that it in turn does not call any other routines. Next down on the call tree, we have isHump. We could see that it's called by main, and then it calls the routines get nearest events, pack arrays, and pack points. If you've profiled your code, you've done your optimization, you definitely want to go back and reprofile. So again, this is from a real life example. We got in there, we're able to improve the performance of get number pack data very, very dramatically. And now we find that it is no longer the hotspot. In fact, it's the routine main that's now the most time consuming routine, clocking in at about 41%. And get number pack data is down to using just 68% of the wall time. Okay, so gprof, it goes way back, 1982. So it's been almost 40 years since gprof was released. So you're probably wondering, is there anything new? So if you're working on an AMD-based system like Expanse, they have a tool called muprof, which provides much more detail than gprof, including a lot of low-level information on things like cache misses, branch miss predictions, etc. So this is going to be a future training topic. In fact, we could spend an entire morning just on uprof. And our team here at SDSC is still getting up to speed on this, but we're expecting as part of our expanse training that we're going to be talking about this pretty soon. So I'm just going to check the chat real quick, see if we have any questions I could answer. Yes, I see some comments there about the dog in the background. Yes, and thank you for posting the link to the GitHub repo. All right. Yeah. So, question: how do we use gprof? So let me just go back a couple of slides. Very easy. I'm going to I'll try to get an example into into my GitHub repo. But it's this line right here, the second bullet, where I say it's very easy to use. When you compile your code, all you have to do is recompile, including the -pg flag. You can include optimization because, say global optimizations like at the -03 level, because gprof does not give you a breakdown of time by statement. It just does it by function. So you compile with the -pg flag, you then run your code just like you would normally run it, and it's going to produce this gmon.out file, which contains all of the sampling data. And then when you run gprof, followed by the name of the executable, in this case I just called it a.out, followed by gmon, you'll then get a file that contains this flat profile and the call graph. So let me just ask, did that answer the question? Good, thank you. And we have a question here from Drago that I guess you're asking, is the slide available to us? Yes, we are going to be posting the slides and the video later. And I'll also take a copy of these slides and I'll put them into the GitHub repo. Okay, so we're going to get into actually doing some optimization. A lot of times when we look at code, we think in terms of portions of code being compute bound versus memory bound. A lot of us get caught up in the processor performance and things like clock speed. But there are going to be some codes, if they're memory bound, where even having a faster processor isn't necessarily going to help. So in a memory bound code, the rate at which the data can be delivered to the CPU is the limiting factor. So our goal is going to be to apply cache level optimizations so that the CPU is not starved for data. In compute bound codes, the performance of the processor is the limiting factor. We can deliver data fast enough, but the processor can't keep up. And in this case, our goal is going to be to reduce the amount of computation done on a given piece of data. And in real applications, we're often going to find that we have to deal with the combination of compute bound and memory bound kernels. So before we start trying to optimize a memory bound code, we need to understand the computer memory hierarchy. So at the very top of the pyramid, we have the registers. This is where we store data that's immediately available to the CPU. So in that next clock cycle, that data is there and it's available. As we move down from the registers, we have multiple layers of cache. Pretty much every processor that I've seen in the last 15 years has 3 levels of cache, an L1, an L2, and an L3. They increase in size as you go from level 1 to level 3, but they're also further away from the CPU. So if data is in the L1 cache, it could typically be accessed within the next few clock cycles. When it's in the L2 cache, it usually takes in the order of tens of nanoseconds to reach that data. L3 cache, a little bit longer. And then if we go all the way out to DRAM, if we don't have the data in cache, then it takes in the order of hundreds of nanoseconds. And then finally, if we're doing out of core computations, where the entire data set can't fit into memory, then we need to go out to disk, and that is much, much slower. So it looks infinitely slow compared to having data in the registers or in the cache. So if we're going to optimize for cache and improve the performance of our memory-bound codes, we need to be aware of two key concepts. There's something that we call temporal locality and spatial locality. So the idea behind temporal locality is that data that was recently accessed is likely to be used again in the near future. So to take advantage of temporal locality, once we have our data loaded into cache, it's going to remain there until it has to be purged to make room for new data. So again, once we have that data in cache, we want to try to reuse it. A key point here is that data the data is loaded as a cache line, so we don't get a single word of data. We get generally 64 bytes of data, and that gets us into spatial locality. And the idea is that if a piece of data is accessed, it's likely that neighboring data elements in memory will also be needed. So to take advantage of spatial locality, the cache is organized into lines, and an entire line is loaded at once. So when we're working with memory-bound codes, we want to try to exploit both the temporal and the spatial locality to minimize data access times. So let's take a look at a one-dimensional array. I think most of you are going to be familiar with one-dimensional and multi-dimensional arrays. In memory, a one-dimensional array is stored as a continuous block of data. So for example, if I had a segment of C code where we're declaring 100 integers. I'm declaring space for 100 integers. Once we allocate that, the first element in that array is going to have an offset of 0. The next element is going to be offset by 4 bytes. Again, we're assuming 4-byte integers here. Next element by 8 bytes, next by 12 bytes, and so on. So optimizing for cache when we're working with 1D arrays is pretty straightforward, and you're probably going to write optimal code without even trying. So let's say we just declared this array of 100 integers, and we want to increment each of those values by 100. So we could create a loop, in this case for int I equals 0 to I less than n, I plus plus, and then element by element increment the array x.
Right.
Oh, sorry, was there a question? Okay, so I'm just looking at the chat here. We have a comment from Lubos. Yes, very good point. Appreciate you mentioning memory bandwidth. Yes, in many modern modern processors, it's really the memory bandwidth that is the limiting factor. And then question from Elijah. So how do you get this information on the screen just before this one? Oh, so this is getting back to gprof. So when I run the gprof command, when I run gprof, name the executable, and gmon.out, that's going to produce a plain text file that will either be written to standard out, or you can pipe that to a file. And then both sets of information, both the profile of amount of time spent by each routine and the call tree are going to be there in the same file, one after the other. And sorry, I can't, Zhao Gei Wang. Well, I talked about IO bound. No, in this talk, I'm just going to be focusing on compute and memory bound codes. But I'm hoping that in a future talk, we'll also get into memory bound. And then finally, a question from Sunsheng Zhu, difference between using dynamic array and using static array in the example. I'm going to say for the purposes of optimization, there's really no difference. We're going to have the same layout of the data in memory, namely that it's going to be contiguous. Okay, so what's happening when we execute this block of code, where we're incrementing these 100 elements of the integer array? So when we hit the first iteration, we're going to load elements 0 through 15 into cache. So those 16 elements will comprise one 64-byte cache line. We're then going to increment elements 0 through 15. And then we're going to load the next 16 elements, 16 through 31 into cache, and then increment those elements. So it looks like we're going to be having a cache miss every 16 iterations, but in reality, the processor designers, they're really, really smart, and they'll do things like automatic prefetching of data so you can grab that next cache line before it's needed. So what's going to happen here is as we're working on those first 16 elements, hopefully we're going to get that next cache line loaded before we need it. Okay, one of the questions that often comes up during these talks is, do I have control over cache? So, for example, is there a command that I could build into my code to say, go out and grab this cache line? No, to the best of my knowledge, there are no programming constructs that give you direct control over cache. That this is something that's implemented at the hardware level. The modern processors are going to directly implement the cache replacement strategies, branch prediction, and prefetch mechanisms. So I'm going to say the best that you could do is just follow the standard practices of exploiting temporal and spatial locality, and in some cases, to choose parameters for your code based on those cache sizes. So multi-dimensional arrays is where things get really interesting. So from the computer's point of view, there is no such thing as a two-dimensional array. This is what we call syntactic sugar. It's provided just as a convenience of the programmer. So under the hood, the array is stored as a linear block of data. The most important thing that you have to remember is that there are two conventions for storing data. There's column major order and row major order. In column major order, the first or the leftmost index varies the fastest. So this is used in Fortran, R, and MATLAB. So let's say I have this 2D array with the elements 1 through 9. The way they're going to be stored in memory is I'm going to go down the first column, 147, down the second column, 258, and then the third column, 369. Row major order is where the last or the rightmost index varies fastest. And this is used in Python, Mathematica, and C++. So again, looking at that same 2D array with the elements 1 through 9, I'm going to go across the first row, 1, 2, 3, the second row, 4, 5, 6, and the third row, 7, 8, 9. So this is going to have really important implications for how you write fast code when you're working with these multi-dimensional arrays. So on the top, I show an example of properly written Fortran code. And note the loop nesting. The outermost loop corresponds to the rightmost index. So I did have a do j equals 1 to n, do I equals 1 to n. And now I'm adding my elements, adding the elements of my array, zij equals xij plus yij. Properly written C code, in this case, we want the rightmost index the very fastest. I've flipped around that loop nesting. Here I have the loop over I on the outside, the loop over j on the inside, and then zij equals xij plus yij. So this is a perfect example of code that's going to be memory bound. There's not a lot of computation going on. All you're doing is adding two values at each iteration of the loop, but you're reading in two words and you're writing out one word. So in this case, it's going to be bound completely by the memory. And having the loops nested in the improper order is going to really impact the performance of your code. So I have an example in the GitHub repo where I've written the code. In this case, I think it was Fortran, using both the proper and the improper loop nesting. I've looked at the effect of using the AMD AOCC compilers, Clang and Flang. These are based on the LLVM project, and the Intel compilers, ICC and iFort. Also looked at the effect of the different optimization levels. So if you look at the documentation for compilers, there are lots and lots of options. But generally, for getting good performance, you're going to focus at what we consider these global optimization levels, -0 through -03. Dash O0 means that you're turning off all optimization. O1 is some limited optimization, O2 is moderate, and O3 is aggressive. And the difference between O2 and O3 is generally that the compiler is allowed to rearrange mathematical operations in such a way that you get better performance, but you don't necessarily guarantee that the floating point results are going to be exactly the same. And the default, that this varies, as we're going to see in the next slide. Let me just check the chat real quick. Okay, question here. What is the best way to learn the cache constraints on your system? How many cache levels, and so on? That is a really, really good question. Oh, I'm sorry, I see that was sent directly to me. I'm gonna put a command in the chat at the end of this talk. It's called lscpu. In fact, here, let me just put that in the chat now. And if you run the lscpu command, it will tell you all about the cache levels, and their capacities. It's not going to tell you the latency, though. And then if you want information on the memory, you're right. Proc mem info is the place to go. But definitely take a look at the output from lscpu. When we're compiling the code, we also want to make sure that we're compiling for our architecture. If you're using the AMD compilers, we recommend using the -march equals znver2 flag. That this means that the architecture is going to be set to the AMD Zen version 2. If you're using the Intel compilers, generally you want to use -xhost, which means that you're going to get the highest level instruction set for the architecture you're compiling on. Okay, so we've been talking a lot about memory bound codes and accessing data in the proper order. So is it really that important? So I have a case here where I looked at a snippet of code that takes two matrices. In this case, I ran it for matrices of size 30,000 by 30,000 in a Fortran code with loops nested in the proper and in the improper orders. So again, this is truly a memory-bound application since we're only doing one addition for every two 8-byte floats that we load. The results on the left are for the AMD compiler, on the right for the Intel compiler. And you see some really interesting results. And I'll go into this in the next few slides. So with the AMD compilers, we find that runtimes improve as we enable higher levels of optimization up to -02. We find in this case that -03 gives the same performance, but also that the default appears to be the same as disabling all optimizations. So we see that the runtimes with either no optimization specified or -00 are the same. And improper loop nesting is always slower than proper loop nesting at all optimization levels. So for example, if we go down to -002 or -03, which is typically what we're going to use when we compile our codes, we see that that having the proper loop nesting results in code that is almost 5 times faster. So it's just an astounding result. If we had done this with a much, much smaller problem, the results wouldn't have been dramatic. But in this case, a 30,000 by 30,000 array is just way too large to fit into cache. So we have to keep going out to memory. Now with the Intel compiler, results are a little bit different. Here, it appears that the default is the same as -02. And also, if we go down toward the bottom rows in the table, -02 and -03, we'll see that the runtimes are identical, which is surprising, because in one case we're accessing the data in the proper order, in the other we're accessing in the wrong order, being very, very cache unfriendly. So what happened was the Intel compiler was smart enough to recognize the loops are improperly nested and reorders them in order to get better performance. If we go back to the AMD compiler, though, Look at the bottom two rows, dash O2 and dash O3. We see that with the improper loop nesting, we never approach the performance of the proper loop nesting. In this case, the AMD compiler did not recognize that the loops were improperly ordered and wasn't able to swap the order of those loops. So some really good lessons to learn here. Um, Making optimal use of cache is particularly important in memory-bound codes. Sometimes the compiler will help you, like the Intel compiler, and sometimes it won't, like the AMD compiler. Also, don't rely on the default optimization. You can see when I compiled with the Intel i4 compiler that if I didn't specify optimization, I got the same results as if I had specified -O2. On the AMD compiler, if I didn't specify optimization, it was like turning off all optimizations. It was like -O0. So make sure that you write your code to be efficient. Don't count on the compiler to help you out, and always explicitly specify a level of optimization. Let me just check the chat. All right, so there's a comment here from M. Dragowski. So when someone decides to port a multidimensional array computation from Python to R, they need to review, update their array computations. Yes, they do. If you were working with multidimensional arrays and you had explicitly written loops to operate on them, you will have to change that. As far as tools to automate that porting, I am not aware of any. There may be some out there. And in fact, if you find any, I would love to know, but I've never heard of any. And then there's another question. Could this be due to Intel having dash fast math enabled by default so that it breaks the IEEE floating point compliance? No, in this case, it has nothing to do with the fast math, which I believe gives you access to faster implementations of trig functions and powers and logarithms and so on. And also there's no floating point compliance, or to put it that's being violated because um, the same set of operations, the element by element addition of those arrays is being done, except just in a different order. So yeah, so the fast math will help you if you're using those intrinsic functions, but in this case, it didn't have anything to do with the results that we saw here. Okay, I'm going to move on. I realize even with the shortened version, I still have too much material for the 1 hour. There are a lot of other loop level optimizations you could do. Loop fusion and fission, loop invariant code motion, peeling, unrolling, blocking, breaking out of loops early, and something I call short loop optimizations. So loop fusion, this is one of the most basic loop level optimizations. It's where we take two loops with the same range of iterations and we combine them into a single loop. This can also give you a good boost if you're working with single loops, especially if they reuse data. So you could see on the left-hand side, I'm taking zi, setting equal to xi times yi plus ai, and then the next loop, I'm working with those same set of arrays, x, y, and a, but I'm just changing the set of operations. In this case, it's x plus y times a. So we could take those two loops, we can fuse them together. And this is going to both give the compiler more content to work with to generate optimal code, and it also it gives us better data reuse. For example, when I have elements 0 of x, y, and a in cache, in fact, in the registers, it's nice to just keep them there and use them again. So here are the results of the loop fusion experiment. Again, this is in the GitHub repo where I looked at an array with 900 million elements using both the AMD and the Intel compilers. And we could see when I get down to, um, we're seeing the same pattern that we did before with the optimization levels, where the performance of the default optimization is the same as no optimization for the AMD compiler or O2 optimization for the Intel compiler. Also, we are seeing a little bit of difference in runtimes between the AMD and the Intel versions. And this is something that I've seen across the board, that the AMD compilers tend to do better on the AMD architectures. But by manually fusing those loops, we typically get about a 30 to 40% decrease in runtime. I'm going to go through the next few slides fairly quickly. We can also do something called loop fission. This is where we take a loop and we split it into multiple loops. This is sometimes going to help if the loop body is too complex or contains too many data streams. It's often difficult to decide if the loop should be fused or split, but if in doubt, you could always try both versions and see which is faster. Let me check the chat real quick. Okay. All right, there's something called loop invariant code motion. And that this is just a fancy term for taking a calculation out of a loop that's invariant, that doesn't change from iteration to iteration, and just pulling it outside of the loop. Sometimes the compiler can do this for you if the loop is particularly simple, but as we've seen, especially with the AMD compiler, don't count on it fixing incorrectly, or I would say incorrectly, but suboptimal code for you. So on the left, we have a case where we're going through element by element, to taking an element of x and adding a constant, square root of c, to it. This is pretty obvious that we don't need to calculate the square root of that constant each iteration. We can pull that out. We can pre-compute the square root of c and then use that result repeatedly within our loop. Square root is a fairly expensive operation, and doing something like this is going to save you a lot of time. But you can also take advantage of this with really much more complex code. This is a stripped down version of a kernel from an application that I worked on with the San Diego Zoo and the US Geological Survey, where we had these 3 nested loops, and there's a calculation that depends on a combination of x and y multiplied by a calculation involving z. So first of all, we see that this quantity, x2, y2, does not depend on the index k on the innermost loop. And likewise, that quantity square root of b times x squared y squared does not depend on the index k. So what I could do is I could take the calculation of x squared and I could move that to the outermost loop nesting. So now we're only doing that calculation nx times instead of nx times ny times nz times. And then we could take that calculation of square root x squared y squared, bump that up one level. So now that's only evaluated nx times ny times instead of nx times ny times nz. And then we can go a little bit further. We recognize that the calculation of z2 does not depend on the indices I or j, and similarly with the exponential. So I could, in this case, I could actually create an entire vector of invariants and use them. So up the top here in red, I show that I'm calculating this vector of what I call z terms. And then in the innermost loop, all I have to do is access the element of that array instead of doing these expensive mathematical operations. Okay, I have another question here. In parallel programming, we need to watch for dependency. Does that come up in any way in maneuvers to optimize loops here? I'm not sure that I fully understand the question. If you want, you can follow up with me after the call. I'm going to put my email in there. There's some subtle problems that we run into once we're working with parallel codes. Okay, loop peeling is an optimization where we take one or more iterations and we pull them out of the loop. so that this avoids calculations associated with special iterations. And it's often used in conjunction with loop fusion when we have loops with slightly different iteration ranges. So again, this is a very contrived example, but if I look on the left, I have my first loop. It goes from I equals 0 to n, and my second loop goes from I equals 1 to n. Also in that first loop, I have one special case. If I equals 0, then I do a division, x divided by y. Otherwise, I do x plus y. What I can do is I can peel off that one special case, iteration 0, pre-calculate that. Now I have two loops that have the same range, and I can fuse them together. And this is going to be a lot faster than the original. Loop unrolling. This is a really common optimization, but it's mostly done by the compiler. Sometimes if you have a loop that just does not have enough content, there's not enough instructions for the compiler to work with in order to generate optimal machine code that keeps the arithmetic functional units busy. So what the compiler will do is take that body and it will replicate it multiple times and then replace the loop with a strided loop. So in this case, instead of doing one operation at a time, zi equals xi plus yi, we replicate that 4 times and we replace a loop with stride 4. One of the reasons I bring this up is you'll see a lot of talk about loop unrolling in the optimization literature, but you will rarely beat the compiler. And manual loop unrolling will make your code ugly and difficult to maintain. And also the best choice for the unrolling depth is probably going to be processor architecture dependent. But every once in a rare case, you might be able to beat the compiler. So this is an example from a chemistry code I had worked on about 6-7 years ago. Very special case where the loops were extremely complicated. You'll see down near the bottom that I have a bracket that says several hundred lines of code not shown, where the loop was just too complex that the compiler couldn't parse it properly and determine what the optimal loop unrolling was. In this case, I was able to manually unroll it by 4x and do better than the compiler. But this is the only example I could ever think of where I was able to beat the compiler. Getting into optimizations where you need to know a little bit about the semantics of your code. Look for opportunities to break out of a loop early. This is generally going to require that you understand what your code is doing. This is a snippet of code adapted from a computational finance application I had worked on. Again, really stripped down, but we had a test within our loop. If y sub I is less than a constant, then we do a calculation. Otherwise, we go on to the next iteration. Working with the developer of this code, we're able to know that the elements of the array y are monotonically increasing. So for example, y0 is less than or equal to y1, which is less than or equal to y2, and so on. There's no way for the compiler to know this. But with our knowledge that y is monotonically increasing, we were able to modify the code, switch things around a little bit so that we test for that condition and break out early, because once we satisfy the condition yi greater than or equal to the constant, we know that condition is going to be satisfied for all future iterations. But looking at another concrete example from a code that I worked on, this was a project I did with NCAR and Los Alamos National Lab on a atmospheric modeling code with something called MPAS, Model for Prediction Across Scales. If you look at the gridding, you'll notice that it's an unstructured grid, and that most of the grid cells are hexagons, but with a little smattering of pentagons and heptagons thrown in. So we're able to look at one of the key kernels. This again is a simplified portion of code where down here in the lower blue box was the original code, where for each cell, we do an iteration over the edges of that cell, regardless of the cell shape. But in a real calculation, roughly 99.999% of the cells are hexagons. So what we did was we split off that common case, that's the blue box on top here. We optimized for that. We basically flattened that loop. We explicitly wrote the calculation, but then we retained the original code for the cases where we don't encounter a hexagon. And I believe that this and a few other optimizations were able to speed up the transport portion of this code by about 40%. And again, it was just by taking a look at what is the most common case and optimizing for that. Let me go to the chat. I see a couple of questions. Okay. Let me move on. Okay, force reduction. This is another place where you can get a really big improvement in the performance of your code. So there are certain operations like evaluating trig functions, exponentiation, logarithms that are really, really expensive. So in the case of exponentiation, look for opportunities to replace with multiplications, especially if the exponent is known at compile time. So on the left, I have calls to the C or C++ power function, right, raising x to the 8th power, x to the 1.5 power. I could really speed that up by explicitly calculating x to the 8th through a series of multiplications, or I could replace the x to the 1.5 power with x times the square root of x. Let me point out that many languages overload the power function. So if you really intend to raise to an integer power, be sure to use an integer argument. So in the case here where I show power of x comma 8, make sure that you write that as x comma 8 and not x comma 8.0. If you have a code that spends a lot of time in trig functions, this is a chance to apply your high school math. Using the trig identities that you would have learned, say, in junior or senior year of high school. Just be sure that if you do this, that the identities apply to all of the quadrants. There was a code that I had worked on about 15 years ago that just by going in and using a few trig identities, we were able to roughly double or triple the speed of the code. Look for hidden opportunities for force reduction. So sometimes there will be an expensive operation in a logical test, and I'll be showing a good example of this in the next slide. In the loop on the left, where we're iterating over the elements of the array x, and we want to know how many times is the logarithm of x less than a constant. Logarithm is a very expensive operation. We can be a little clever here, though. We can take the exponent of both the left and the right-hand side of that comparison and replace log x less than c with x less than the exponent of c. Pre-calculate that once and then reuse it, and that's going to save us a lot of time. So in the GitHub repo, I have a little toy problem in there where I randomly generate n particles. In this case, it was 100,000 particles in a unit square, and then just test by brute force how many of those particle pairs are separated by less than a specified distance. In this case, 0.01. With the force reduction, I compared x squared plus y squared directly to distance squared. Without the force reduction, I compared the square root to the distance. And you can see here that we get an almost 3x speed up for that chunk of code by avoiding the calculation of the square root and just testing the distance squared rather than the distance directly. Okay, so I am almost out of time. These slides we posted. This is where things get really, really interesting. Inter-procedural optimizations. Up until now, we've been looking at individual routines or individual chunks of code. But inter-procedural optimizations are where we take a high-level view of the entire program, spanning across multiple functions. These are often a lot more work. They require that you have an intimate understanding of your code, um, recognizing operations, say, that are repeated in the same sets of data from one invocation of a function to the next. But again, they could give you a really big payoff. I'm just going to flip through these slides. This was an example that I talked about earlier in flow cytometry. And we had a function that was called 5 times in a row with slightly different arguments. We realized that a lot of the work being done was the same each time. So we were able to pre-compute results. Again, this required that we use a little bit more memory, but we could then save those results. And instead of doing all of the additional calculations, we could just reference the elements of those arrays. So we are good. We're right at the top of the hour. Just to wrap up, optimizing your code reduces time to solution, saves energy, and it makes those valuable compute resources go further. Before you get started, make sure it's worth your effort. Does the code use a lot of time? Is it widely used? Is it going to have a life beyond your one research project? I didn't get into this. I cover this topic in the full half-day workshop. But when you do optimizations, they can potentially change the results. For example, if I replace x to the 1.5 with x times square root of x, I'm going to get numerically very, very slightly different floating point results. I'm not going to say that one result is more correct than the other, but ask yourself how critical reproducibility is. Most codes do not need bitwise reproducibility. We talked about profiling. Definitely profile your code when you start off, optimize the code, and then if you're going to keep working, repeat the profiling so that you know what the new hotspots are. Take advantage of the optimized libraries and the work of others. We like to say that great programmers steal great code. Try to avoid the mindset that you're cheating if you're using somebody else's work. The folks who develop eigenvalue solvers and linear algebra routines, they do that professionally for a living, and you're not gonna come close to what they do. Take advantage of that and focus on your science. Know the capabilities and limitations of your compiler, but don't rely on the compiler to fix your bad programming practices. We saw that the Intel compiler was pretty good about recognizing when you did things that were suboptimal, but the AMD compiler didn't. So always try to write good code. Optimizing cache is critical, especially for these memory-bound codes. And the biggest payoffs sometimes come from having a deep understanding of the semantics and the structure of your code. This is where you could really get into the inter-procedural optimizations. And with that, I will wrap up, and I'm just going to check the chat, see if there are any more questions. Okay, so there's a question from Robert Cady. Why are power functions so expensive? Yeah, so there are certain operations that you could do directly in hardware, like additions and multiplications, and actually division and square root also. The power functions and trig functions actually have to be done in software. It's a whole series of operations. So I'm going to say just compared to the basic floats, floating point operations of addition, multiplication, subtraction, and so on. There's just a lot more that needs to be done. There's a question here: is inlining a big help versus the overhead of function calls? Yes, absolutely. So I didn't cover that in this talk. There's a technique called inlining, which is where you take the body of a function that's being called by another routine, and you just drop it directly into that routine. Yes, that can save you. That can make your code much more efficient. And it is one of the things that a compiler can do. But there are cases when inlining won't occur, especially if the body of the function being inlined is complex. So I would say if it's a really critical piece of code, I would just go ahead and do it manually. Have a question. Have you had any experience with an optimization with one compiler? Turns out to be worse with another compiler? Um, I think you're getting at, is there a, yeah, getting at the difference in the quality of the code that is generated by different compilers. Yes, you're often going to see a difference. So in fact, I didn't show it in my slide deck, but on this force reduction example, I also did this with the Intel compiler. Very, very simple piece of code, and the Intel compiled code was about 5 times, took about 5 times longer. And that's something that I'm still trying to figure out. It could be that the Intel compiler that doesn't fully understand how to make optimal use of cache. In this case, when I only had 100,000 particles, that's a problem that should be able to fit entirely into cache. So yes, absolutely. Now we have a question for an MPI code. Would running on one processor be the same as running it serially, or would there be some MPI overhead? It it all depends. So sometimes in a lot of codes there is some MPI overhead, especially at the startup and the end, where say some calculations are being done on one processor and then broadcast to the others. If you really want to profile an MPI code, there are more advanced tools like Tau, which do both profiling and tracing, which will um, show you where your code is spending time in communications. For what we talked about here, if you had a code where we already understand the communications pattern and it scales well, you could use, say, something like gprof on that code, and you will get a profile for each process, and you could use that to optimize the serial code. But again, running on one processor versus multiple processors, it's going to depend a lot on the application. And one second, let me find my mouse, and there's a question here. Okay, so yes, so there's a question from Yogesh. Are there any tools to identify the code with complex nested loops that may be parallelized? Oh, I believe that there are. I remember some of the Intel tools could recognize codes that could potentially be parallelized. And I'm not familiar enough with the AMD tools yet. Okay, a question from Chris Gross. How can I study whether or not the data my code is working on is held in L1 cache or a higher level memory? So I mentioned earlier in the talk, right after I got done with gprof, that there's a tool called muprof developed by AMD, which will give you really, really detailed information on things like cache misses. So in that case, you would be able to look at that output and figure out if you're having frequent cache misses. Also, as far as your code fitting into L1 cache, you would have to look at the size of the L1 cache and the size of your data set to figure out if it would fit in there or not. And again, I'll just put it into the chat box again. There is a command called lscpu that will give you information about the cache sizes. And let me see if I can answer a few more questions before we wrap up. Okay, Prof, I think you mean gprof, work for parallel code, shared or distributed. So it works great for distributed codes. You'll get a profile for each process. For shared memory codes, it's a little more complicated. Um, and I didn't put in this presentation, but there are some hacks for using gprof with a threaded code. And with that, I think I'm going to have to wrap up because we're already 6 minutes past the hour. Thank you everybody for joining me today, and we will get these get the slides and the video posted soon. Thank you.
Thanks, Bob. Bye, everyone.
Thanks, Bob. Thanks, everyone, for attending.